Uh, okay, perfect. Um, I so just a little bit about me. I've been at De Anza for about 4 years now. Prior to that, I got my master's degree at San Jose State. I was in meteorology. While I was there, I was studying land surface processes and how those influence Earth's climate. Um, and one of the things I realized while I was there was that there were a lot of hands in that sort of climate science pot, but not a lot of people were going beyond that and talking with people about climate change, actually going out and taking what they knew and taking what they were working on and sharing it with others. And for me, something that I got really passionate about was this idea that this stuff is really important. I mean, this is in a very real sense life or death in so many ways. And yet, I think oftentimes people don't know that because it's not something that is sudden. It's not something that you see in your face the moment you step outside necessarily, like unless there's a big catastrophe like the fires of this last year, which my background, this is actually the sunset during one of the last big fires. This was actually taken in Monterey. And if you take a look, that sun just looked like a big red dot. It was so eerie. Um, and the fires that we've had this past year, those kind of fires have been becoming quite a bit more common over the past few years. And while it's very dangerous for us to say something like, okay, well, we've had a few fires, climate change, um, we have to look at a pattern that has been going on. And there's definitely been a pattern of drier winters, warmer summers, and more fires. And so it is at least important to kind of think about, well, how does this actually link to our warming world? So with that being said, um, let me jump in with my presentation. So one of the things I want to say is that I put together a presentation. Anybody who's taken a meteorology class with me, some of what you might see here might be a little bit familiar with you. I tried my best to sort of um, add a little bit of a different flavor to it, add a little bit of a different spin to it so that it wouldn't put anybody to sleep if they've sat through it before. Um, but at the same time, I really do hope that some really cool stuff can be talked about here. One other thing I really want to stress is that I want this to not just be like a lecture. I want this to be a discussion. I would love I would love for all of you to ask me questions. I would love for it to be an opportunity to chat about some of what's going on here. Um, and I'm pretty much an open book for all of you. I mean, I can't pretend that I know every single answer in the world. But I can also point you in the right direction in many cases. And if there's something that I can't answer, we can figure it out together. Um, so without further ado, let's jump in. So things I always love to do in my classes when I actually teach about, or actually I do this pretty much at the beginning of every class. I start with what I call a warm-up question. It's basically an icebreaker, and the purpose of it is just to get people to kind of think about what we're talking about that particular day. Um, I had actually set up a Padlet to do this. I don't know if anybody's used Padlet before, um, but I actually think, based on the number of people in the room, I wouldn't mind if people just type their answers into chat. And if you want to remain anonymous, you can private message me your answer and I can read it out. And I won't share your name or anything. But I just want to know, what comes to mind when you think of climate change? Like, and let me stress right now, don't feel like you have to don't feel like you have to think a whole lot about this. Like, when you hear the words climate change, what immediately pops up in your head? Um, Open up that chat box and type in some thoughts. What comes to mind when you think of climate change? Aki, one of my students, greenhouse gases. No more snow, no more winters, no more cold. Loss of habitats. Mhm. rise in natural disasters. Okay. What else? I love it. So I'm hearing greenhouse gases, no more snow, no more cold, loss of habitats. What other words, what other thoughts pop in your head when you hear climate change? Extreme weather. Hmm. I love it. Longer seasons. Yeah, I was actually just reading an article earlier today, and I think it was kind of a hyperbolic article. I found it on IFL Science that said that by 2100, summers are going to be 6 months long. Um, though our astronomical seasons wouldn't actually change. It's just going to feel like summer's lasting longer. Um, Extreme weather, longer seasons. Um, Anything else that comes to mind? I mean, I love what I see here so far. I love loss of habitat, or I don't love that, but you know what I mean. Vegetation is affected, absolutely. Um, Both in terms of ecosystems and even in terms of our own crops, which ultimately affects our ability to feed people. Um, well, let me throw a little wrench into this question. Somebody had mentioned no more cold. So, how would you explain what happened in Texas a few weeks ago? How can that be explained in a warmer world? What if somebody came up to you and asked that question? Like, so what's the deal with Texas? If the earth is warming, why was Texas so cold? No, I'm going somewhere with that question. Um, I'm just curious what your thoughts are about that. I know anybody who's taken a class with me knows that I kind of poked the bear a little bit. Um, we're going to two ends of the spectrum. So maybe more extremes, and somebody else mentioned more extreme weather. Maybe we're seeing more extremes. What comes to my mind is because California winters have been very warm. Yeah. So one of the reasons why I asked that question is a former high-profile government figure used to post on a social media account, "Hey, it's really really cold outside," or "Record-setting cold in Chicago. Global warming is a myth." And a lot of people buy into that. They go, "Wow, that's so true." Um, it's so true, but actually not quite. So let's jump in and actually talk about what is going on. So first off, one of the reasons why I'm so passionate about talking about this is because it can be very confusing. You hear the words global warming and climate change oftentimes used interchangeably. You hear a lot of other terms: greenhouse gases, pollution, ozone, warming, extreme weather, environmental damage, ecosystem damage, angry weather and angry seasons. I like that. Um, you hear all of these different terms, and oftentimes we kind of get lost in this alphabet soup of all of these terms, and we kind of get muddled in them. What makes it even worse is that climate change has become very much politicized. Um, for example, I don't know how many of you have ever heard of the movie An Inconvenient Truth. Um, it was a movie that former Vice President Al Gore did in 2005. A few years ago, he did a sequel to it called An Inconvenient Sequel. Um, and I loved the movie and I loved what he did. And I thought what he explained things very well. The thing that I hated about it, though, was that he is a high profile Democrat, which now immediately means half of America, boom, tunes him out. He's a Democrat. He's not on my team. I don't want to hear him. Meanwhile, on the other side, we have other high profile politicians actually actively trying to speak out against global warming. Um, our former president, Donald Trump, actually took us out of the Paris Climate Agreement, a global climate agreement. Um, and we are the second biggest carbon emitter in the entire world. And um, we have emitted the most overall in the entire world. And so the success of the Paris Climate Agreement really hinges on our involvement. And yet he took us out of it. Now that has been changed now under the new administration. We are now officially back in the Paris Climate Agreement, which that makes me really happy. Um, but yeah, the reality is that this topic has become overly politicized, um, which kind of happens to any sort of big topic in the United States. Obviously, COVID's become overly politicized. There's been so many other major moral issues that have been overly politicized. I obviously don't want to go into that, but this topic has become overly politicized. But the fact of the matter is that it is serious. Um, the truth is that as our world continues to warm and as our Earth system changes due to that warmth, it could have very dire consequences. Things such as droughts, things such as more wildfires, things such as more extreme weather, hurricanes such as Irma, Maria, Harvey becoming more common. And it has consequences. So this is what I'm showing right here. This is Lake Mead. Um, if you don't know where Lake Mead is just east of Las Vegas. It's where the Hoover Dam is. And Lake Mead is a reservoir that basically allows much of the desert Southwest to even exist. One of the reasons why Las Vegas is even a city is because of Lake Mead. And we've actually seen Lake Mead and really the whole Colorado River basin basically dry up. And this was in 2010. I should mention that the following decade, 2011 to 2020, was extremely dry. So the fact is that we're getting drier out here in the West, at least here in the Southwest, for many reasons. And I'm going to go into a few of those reasons why right now. But so this does have consequences if we're not careful. But that being said, what actually are we talking about? When I mention climate change, and when people hear that word, it is a very loaded, very politicized, very triggered word. And oftentimes it's used interchangeably with the term global warming. So the fact of the matter is that global warming and climate change are actually two completely different topics. They're two completely different ideas, but they're oftentimes used interchangeably. And I think that's where some of the misleading mentality comes in. So let me explain why us as climate scientists really kind of shy away from the term global warming. So first off, global warming is happening. I actually have a video that I pulled from NASA earlier that actually shows how the Earth has warmed over the past 140 years. But global warming represents the increase in global average temperature due to human activity. And there's a lot of data suggesting that we have warmed substantially in the last 140 years. The IPCC, the Intergovernmental Panel on Climate Change, that's sort of the UN's bigwig scientist body that studies and predicts and diagnoses climate change, has actually concluded, and this was in their most recent report, a new one will be out later this year, that the Earth has actually warmed 0.85 plus or minus 0.2 degrees since 1880. Just to spell out what this actually means, this means we can say with a 95% statistical confidence, that's kind of considered that is considered the gold standard in statistics, that Earth has warmed somewhere between 0.65 and 1.05 degrees Celsius since 1880. Now, I know what you're thinking. Chances are we may warm a degree or two just while I'm talking outside. A change in temperature by a degree or two doesn't seem like that big of a deal. But when this is happening on a global scale, this means that there's a lot of additional heat that has to be thrown in our system for that to happen. And so that does actually disrupt things. Not only that, but this warming isn't being felt everywhere the same way. And it's because of that that global warming is actually a very misleading term. And I think it becomes so easy for people to say, oh, well, look at Texas. They froze like snowpocalypse. It was a big deal. I have family that lived there. They were without power for a week. Um, okay, so how does that vibe with global warming? And it's really easy to sort of then say, okay, well, it doesn't. But here's the thing though, global warming is an oversimplification of the issue. So let me explain what I mean. Let's say this was one of my classes and I just gave you all a test. And let's say the class average of the test came back and it was 80%. And I said, all right, everybody, so the class average was an 80%. I'm going to give you all an 80 on the test. So that's what I'm going to do. The class average was an 80%, so I'm just going to give you all an 80. Would that be accurate? See some people shaking their heads. That wouldn't be accurate. If, yeah, I mean, think about that. Taking one metric, one number to summarize an entire situation while ignoring the individual pieces. You may have somebody who got 100, and suddenly me giving them an 80 would be screwing them over. I would be angry if I was that person. I would go to rate my professors and leave a bad review, and it'd be a mess. And by the way, I would never do that. But that's really what we do when we talk about global warming. We are, in a very real sense, taking everything that's happening in our Earth and we're summing it up in one metric. And so we're missing a lot of the picture. The fact of the matter is that 0.65 to 1.05 degrees Celsius is not evenly spread out, just like that 80 on the test would not be evenly spread out. Instead, some places are warming a whole lot more. Other places aren't warming at all, and believe it or not, some places are even cooling. Let me say that again. Some places are even cooling. And so when we kind of cling to this global warming term, that's almost like saying all horses are pink and then showing me a green horse. It's very easy, very quickly, to poke holes into that. That being said, the term global warming has kind of been pulled back, at least by climate advocates. And the term that's oftentimes used now is climate change. The reason why we use that term now, it's not meant to deceive people. It's actually meant to clarify the situation. Okay, the class average was an 80. That doesn't mean everybody did well. There may be some people who I need to meet up with and help out and see how I can support them and go over the test with them. And well, the same is true with Earth's climate system. Okay, average temperatures have risen by 0.65 to 1.05 degrees Celsius, but individual locations experience that differently. And some locations are indeed getting warmer. The North Pole, for example, is actually seeing the bulk of our excess warming. And I'll show you what I mean in a moment. And I'll also explain why. On the other hand, other places aren't seeing any warming at all. Many areas near the equator are seeing little, if any, warming. And some places are even cooling. For example, the North Atlantic. While we have been baking in record warm temperatures across most of the world, the North Atlantic has actually seen this sustained period of cooling. So global warming isn't a thing, right? No, the Earth is still warming, but that warming is causing consequences at different places. So basically, Earth's average temperature is indeed going up. That is a fair statement to make. When you actually take a look at everywhere on Earth, when you take a look at all of our weather stations, our buoys, and we have thousands scattered all around the world in the oceans, as well as weather stations on land and satellite data to fill in the blanks. We have seen a very marked, very sustained upward trend in the past roughly 100 years. But again, not everywhere is seeing that evenly. So this is 2020, which, by the way, 2020 tied for 2016 as the warmest year on record. The global temperature anomaly, meaning the difference from average. So if I gave a class average and it was 80, a difference from an anomaly would be something that is other than 80. Well, in 2020, we were tied for the warmest year on record on Earth, with an anomaly of approximately 1 degree Celsius. However, if you take a look at this map right here, what this actually shows are anomalies, differences from average across the entire world. Oh yeah, I love how 2020 is one of the warmest when everyone said COVID helped the environment. Yeah, no, we're actually still setting new carbon dioxide records. In fact, I'm going to talk about that in a few minutes. But no, COVID barely put a dent in this problem. It barely put a dent in this problem. And I'll explain partially why in a little bit. But if you actually take a look, different parts of the world experienced this warming differently. Interior Siberia saw warming above 5 degrees Celsius above their average. Interior Siberia is actually one of the coldest places on Earth, even colder than the North Pole. And yet they've seen a lot of warming. Much of Europe saw above average temperatures. Much of the US saw near average or slightly above average temperatures. Parts of interior Canada saw cooler temperatures, but there's actually one place that's particularly concerning. This blob of cooler than average temperatures has actually been there for about 10 years now. And here's what's actually happening there. Has anybody ever seen the movie The Day After Tomorrow? One person says that they've seen it. Okay. People have seen it. It is a piece of fiction, and depending on your taste in movies, you may say it's something else, but it is a piece of fiction. There is a lot of science in it, but there's actually one really good piece of science. One piece of science that I will actually compliment them on. They talked about something called the North Atlantic Current. The North Atlantic Current carries warm ocean waters from near the equator up along the east coast of the United States and right up into this area. One of the things that drives the North Atlantic Current, though, is that once this area gets the heat from the North Atlantic Current, all of that water's got to go somewhere. But what happens is it becomes salty, it becomes dense and salty, and begins to sink down into the deep ocean. Well, in order for it to be able to sink, it has to be salty. But right next to this area is home to some of the most ice in the world, Greenland. Greenland has a lot of ice, and this ice is melting. And all of that melting ice is dumping right into this region making the water there less salty and therefore less prone to sinking. That is actually slowing down the North Atlantic current and actually slowing down the exchange of heat between the equator and the North Atlantic. Now, right now, thankfully, what we're seeing is mostly isolated to this patch here in the North Atlantic. However, if this were to completely shut down, it could actually shut Europe off from a lot of its heat source, which Europe is actually seen, or Europe is actually overall, Europe's latitudes are similar to those in interior Canada and Alaska, and yet Europe is nice and warm. It's actually postulated, it's actually feared that if this current were to shut down, we could actually see Europe losing heat. It could actually result in Europe becoming cooler. And that was actually mentioned in The Day After Tomorrow. That was like the only piece of science that they got right. Everything else was like huge ice hurricanes that killed people and froze them to death. That stuff's all wrong. But the possibility that this current could shut down is actually a real concern. But that just goes to show you how this warming that we're seeing can actually result in some places cooling down. So even though global warming is true, it is happening, it is absolutely happening, if you stop there, it is misleading. That being said, okay, so what's causing all of this? What is actually causing global warming? So a few people mentioned in chat, I heard people mentioning greenhouse gases and the greenhouse effect. That's one thing that can cause global warming. What are some other things that can change our climate in addition to just warming? Well, there's all kinds of things that can actually change our climate system. Solar activity. Did you actually know that our sun goes through this period of additional solar activity where it has more sunspots, it becomes a little bit brighter. Essentially, it becomes a little bit brighter, gives off a little bit more radiation, and then becomes a little less active, becomes a little more active, becomes a little less active. Oftentimes, that is seen as something that can have effects on Earth's climate. Not so much solar flares, I'm more talking about sunspots. Solar flares do happen, and if we actually see like a big solar flare, that could actually trigger what's called, that could actually be a part of what's called a coronal mass ejection. Usually those are pretty just like, almost like a burp. It's almost like the sun just burped. It doesn't actually cause a prolonged warming or cooling. It's usually just like one big burp, and that can actually wreak havoc on our electric grid, which would not be fun. But solar activity does go through these periods of more active, less active, more active, less active, for a period of about 11 years. Other things that can change Earth's climate, Earth's motion around the sun. Believe it or not, Earth's orbit is not a perfect circle. It actually does change shape over time. Earth's orbit changes shape over time. The degree of Earth's tilt changes over time as well. And where the tilt is pointed at changes over well. All of these take tens of thousands to hundreds of thousands of years to happen. So they're very, very slow considering our human timeline. Continental drift. I don't know how many of you know this, but in about 10 million years, Dodgers versus Giants will basically be a crosstown rivalry. Because in about 10 million years, we're going to be a lot closer to we're going to be a lot closer to Los Angeles. LA and San Francisco are going to be a lot closer to each other. Kind of an interesting fact to think about. Well, continental drift changes Earth's ocean land distribution, and that has changes on Earth's climate. Antarctica actually froze because of that. But that takes millions of years. If you want to see a plate move, a continental plate move, hold out your fingers, watch your fingernails grow. It's about how fast it happens. So that's very slow. And then other things such as cataclysmic events. How many of you have ever heard of the Yellowstone volcano? Beneath Yellowstone National Park, there is a giant supervolcano that erupts roughly every 600,000 to 700,000 years. The last time it erupted was 640,000 years ago. Yes, that means we're due. Now, that doesn't necessarily mean that we're going to see a volcanic eruption like between now and tomorrow. There would be a lot of advance warning. And when I say we're due, I mean in geologic terms. So that could be tens of thousands of years. But those kind of things also have sudden drastic impacts on Earth's climate or asteroid impacts. I'm sure we could ask our old friends, the dinosaurs, how that changed their climate. But here's the thing with most of these cataclysmic events. They're very short term. What I mean by that is that you can get a volcano, it can erupt, it can eject a lot of stuff into the atmosphere. That stuff may hang out there for a few years, cooling the earth, but eventually it all settles back down. And while there may be some differences afterwards, things kind of just go back to the way that they were, except for usually ecosystems have crashed and we've seen mass extinctions and stuff like that. Supervolcanoes such as the Yellowstone volcano occur roughly every 10 to 100,000 years. Major volcanic eruptions, like volcanic eruptions that we've actually seen in recorded history, such as Mount Tambora and Mount Pinatubo, occur every few decades. These kind of eruptions are actually capable of cooling the earth, but only for maybe 6 months to a year. So we see a little cooling period and then we just go right back to where we were. And then smaller eruptions such as Mount St. Helens or what you see on the Hawaiian Islands, those are actually very minuscule in their impact. And then finally, asteroid impacts. They don't happen very often, at least not to the scale that could actually change Earth's climate. What I'm really trying to say here is that the fact of the matter is that these aren't the things causing this. These either take too long, don't last long enough, or are too minute. So what is causing all of this? Well, I'm pretty sure that most of you knew where I was going at with this, but the answer is human activity. Humans have been around now on this earth for tens of thousands of years, so a few tens of thousands of years. But we've really had our biggest impact in the last 200 years as human population has exponentially grown. We went from 1 billion to 2 billion to 3 billion to 4 billion. Now we're at 7.8 billion and just growing and growing and growing. The rate of growing is slowing now, but our population is still growing. And as it grows, the bigger our population gets, the bigger the impact. Which is one of the reasons why we've only seen these impacts in the last 150-ish years, because we've only had enough of us to have these kind of impacts. So a common argument, I actually just wanted to go back to sunspots really quickly, because they're the only thing that operates on a time scale similar to what we've seen in terms of global warming. They're the only things that operate on a similar time scale. So can they explain the consequential climate change that we've seen due to global warming? And the answer really is not really. And there are two main reasons why. Reason number one, and I actually got this from NASA, they know a thing or two about a thing or two. They have actually suggested that at most, solar variation can be responsible for at most 0.3 of a degree of warming, or 0.3 of a degree of variation. Just as a friendly reminder, we have warmed between 0.65 and 1.05 degrees since 1880. So that's the first reason why. Ultimately, solar activity is not enough to explain it. The other thing is that if solar activity was the primary driver, we wouldn't be seeing this sustained increase, this upward trend. Instead, we would see something that has a much more wave-like pattern to it. We would see something that's much more up and down, up and down, up and down. But that's not what we're seeing. Yes, we do see a little variation from year to year. That still happens, but the overall trend is just up, 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 and up. So sunspots can't do it. Sunspots cannot explain this. And a lot of people say, well, did you know we're headed towards a solar minimum soon? They're calling it the grand solar minimum. Some people are calling it the Maunder minimum because it's based off the last big solar minimum we had in the 1600s. The answer there is, even if that were to happen, the amount of warming that we're experiencing would be way more than enough to offset it. So sunspots can't do it. They cannot be responsible for what we're experiencing. And none of the other things happen quick enough to be responsible. So really the answer comes down to, as I'm sure many of you know, the greenhouse effect. So here's how the greenhouse effect works. How many of you have ever gone into your car on a sunny afternoon? Your car's parked out in the sun on a sunny afternoon. How's the interior of your car like? Yes, and the belt buckle sucks. Yeah, it's hot. Absolutely hot, melting hot. I love it. Yeah, no, it's very, very hot, right? It doesn't even actually have to be that hot outside, but it's still very, very hot. Well, the reason why are the windows on your car. The windows on your car are transparent to most visible light, which the bulk of solar energy actually comes in the form of visible light. Not just visible light, there's also ultraviolet, near infrared, and a cocktail of other wavelengths of radiation, but really the bulk of it is visible light. And your windshield and your windows are transparent to that visible light. So it just passes right through. So all of that intense light from the sun passes right through. And as it then enters your car, it heats the interior of your car up. If you have a dark interior, it heats it up even more than if you have a light interior. But it heats it up. Well, as a result, now that your car has more heat in it, now that it's heating up, your car is also giving off more heat. The thing, however, is that your car is giving off a different kind of heat called infrared heat. And infrared heat is not able to pass through that glass. That glass that was oh so transparent to sunlight absorbs and traps that infrared heat that your car is giving off, keeping it trapped inside your car, keeping you nice and warm. Well, believe it or not, there are these little gases in our atmosphere that behave very much the same way. Specifically, carbon dioxide, methane, water vapor, ozone, nitrous oxide, and a few other key greenhouse gases trap heat in our Earth. And that keeps our Earth warm. Now, let me just ask this really quickly as a climate alarmist, which I identify as that. I identify as a climate alarmist. How many of you have ever heard that greenhouse gases are bad? You watch an infomercial, you read a pamphlet, you see somebody say something like, greenhouse gases are bad, greenhouse gases are evil, greenhouse gases should be murdered. No. Yeah, high school science. No. Greenhouse gases are good. Let me say that again. Greenhouse gases are good. If we had no greenhouse gases, Earth's average temperature would be on average 59 degrees cooler than it currently is. Think about that. I'm looking at my weather station right now. It's 57 degrees outside right now. Obviously, just like with climate change, that heat would not be distributed, or that difference would not be distributed evenly. But just for a crude example, let's just take our current temperature, subtract 59 from it. My weather station right now says it's 57. If I subtract 59 from that, it would be a temperature of -2. I don't know about you. I've actually experienced a temperature of -2 before, and I would not wish it on my worst enemy. It is just as bad as a temperature of like 110, 120. It is just as stifling. It is just as crippling. It is just as burning. Oh, it's bad. Humanity would not be able to survive in that kind of condition. We just would not be able to. We wouldn't be able to grow plants. We wouldn't be able to raise livestock. It'd be a bad thing. So greenhouse gases are a good thing. However, please forgive me if I mispronounce your name. However, as Wei said in chat, just like anything, I love coffee. If I drink coffee nonstop, I would be jittery, I would feel bad, I'd feel sick. Or just like your favorite food, I love sushi. If all I ate was sushi, breakfast, lunch, and dinner, breakfast, lunch, and dinner, breakfast, lunch, and dinner, I'd get sick of it, and I probably would get sick, period. Too much of a good thing makes it bad. And that is exactly the problem with the greenhouse effect. The problem is that we now have more greenhouse gases than we have had in a long period of time. In fact, we now have more greenhouse gases, more carbon dioxide specifically in our atmosphere than we have had in the last 400,000 years. So we are way above where we've been in geologic time. So that's concerning. That's really concerning. Furthermore, there's actually a lot of evidence from the IPCC that carbon dioxide has the biggest effect. So I usually show this in my intro to climate change class. I've shown it in my weather and climate processes class before as well. And I've actually given it to some statistics teachers because there's a lot of really cool statistics you can do with this. But let me explain the TLDR of it right now. So each one of these things is what's called a radiative forcing. Basically, it is a change in Earth's energy budget caused by the presence of this particular thing. Caused by the presence of this particular thing. Wherever you see orange, that represents warming. Wherever you see blue, that represents cooling. And these are all anthropogenic human activities. So things like excess carbon dioxide emissions, excess methane emissions, other halogenated gases, as I mentioned, other short-lived gases such as ozone. Over here, aerosols, that's the stuff that whenever you see smoke or any kind of pollution, it's usually made up of these little solid or liquid particles called aerosols. And if you take a look, many of these either have a small change or their change is very uncertain. Wherever you see something such as right here where the bar is both orange and blue, we can't say with statistically confidence that that causes either warming or cooling. There's not enough statistical evidence to suggest it. So when you add all of these things up, though, really the bulk of our warming, right here, carbon dioxide. Carbon dioxide has the biggest effect. Methane has the second biggest effect. And when you put these two things together, pretty much almost all of the net warming due to human activities can be attributed to just those two things. everything else kind of cancels itself out. Land use changes, changes in what's called albedo, which I'm going to talk about in a minute. Each of those things actually somewhat gets canceled out. But when you actually take a look at carbon dioxide and methane, they're having major impacts. They're having major impacts. And yeah, carbon dioxide is on the rise. Carbon dioxide is on the rise. This is the world famous Keeling curve. This is data that's taken at the Mauna Loa Observatory, hosted by the Scripps Institute of Oceanography from UC San Diego. And what you see is actually a sustained upward trend. Every single year, we are reaching newer peaks and newer peaks and newer peaks. And guess what? In 2020, in COVID year, in a year where we actually had to cut back due to decreased productivity, due to decreased commutes, we still hit new records. So carbon dioxide is still on the rise. Usually I also walk through, if this was one of my classes, I would walk through and kind of explain what this zigzag pattern is. I like to call it the Bart Simpson's hair analogy. This is actually due to seasonal changes. Every single year, obviously, in wintertime, trees fall asleep. We get our pumpkin spice lattes. We wear our nice warm sweaters. We take pictures and post them on Instagram. And during those times, carbon dioxide concentrations go up. Then in the spring, trees begin to bloom, flowers begin to bloom, things begin to wake up. Carbon dioxide concentrations go right back down. And so we do kind of see this up and down, up and down, up and down. But when you actually take a look at the bigger picture, we are seeing a sustained increase in carbon dioxide concentrations. But, and I say that with two T's, unfortunately, carbon dioxide is not the only thing at fault here. Methane is a bad issue as well. Methane is a bad issue as well. And we have seen a pretty substantial increase in methane concentrations as well. It leveled off a little bit in the early 2000s, but as economic growth has really taken off in many areas, in many developing economies over the past roughly 10 or 15 years, many of those economies have actually transitioned over to meat-based diets. They love steak, they love burgers, they love beef, just like we in America love steak and love burgers and love beef. That requires a lot of cattle. And in order to even get that cattle, guess what you have to do? You have to make pastures. In order to make pastures, you have to chop down trees. So we're chopping down trees and we're replacing them with methane burping and farting cows. Methane burping and farting cows. And those methane burping and farting cows release a lot of methane. Now, here's the thing about methane. Methane is not as present in the atmosphere as carbon dioxide, but depending on who you talk to, depending on what textbook you read, depending on where you hear it from, you will hear somebody say that it is between 20 to 30 times as potent as carbon dioxide. What that means is one molecule of methane can hold the same amount of heat as 20 to 30 molecules of carbon dioxide. So even a little extra methane is really, really bad. So that's something that we're kind of getting worried about right now. And with the increase in demand for cattle, we're seeing methane shoot up. So what does all of this actually mean? Tying together each of these things, because I do actually want to bring it back home to California and then kind of talk about what we can actually do. So an increase in temperatures doesn't really seem like that big of a deal, right? 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 It is a big deal. Here's why. First off, many ecosystems are very temperature sensitive, such as coral reefs. Coral reefs are very temperature sensitive. Even just a slight change in ocean temperatures can wreak havoc on coral reef populations. Now, because I'm not an environmental scientist, I'm a meteorologist, I focus more on the physical side of things, not so much the environmental side of things. Yep. Um, I don't know as much about ecosystem collapse, but I will say that ecosystems that are sensitive to changes in temperature are being threatened right now. And exactly, fish don't detect predators as well, don't detect predators as well and get eaten. Exactly. Yeah. Many of the evolutionary features that animals have actually had to help them survive and adapt to their surroundings are now being taken away from them because temperatures are changing. Each one of those things has very big consequences. Um, so even just a small variation can trigger massive destruction. Now, in my wheelhouse, as I mentioned earlier, the North Pole is seeing the most warming. And I'll explain why in the next slide. But it is important to note that the North Pole is actually seeing the most warming here on Earth. That areas up there in the northern part of our planet are seeing the most warming. Weather patterns are being severely disrupted by temperature changes. Weather is very temperature dependent. And so when we actually add more heat into our Earth system, that throws our weather patterns off. That makes them go haywire. Why did Texas get so cold a few weeks ago? Our polar jet stream, which is a part of our global circulation, went haywire. And it just suddenly made this big drop, what's called a trough, and it happened to be right over the central part of the United States. And boom, all of a sudden, places that had never seen temperatures that cold were getting record cold temperatures. But it's because our jet stream went haywire. Now, that being said, why is the North Pole getting warmer? Well, here's basically what's happening. I actually shot this video for my introduction to climate change class. It's a few minutes long, but it's worth taking a look at. Um, tell me if you can hear it. Let's see here.
Recorded. Okay, it is being recorded. Okay.
Can you
Hi,
hear this?
everybody. This thing's on.
Awesome.
So what we're talking about in class today is what is called a positive feedback loop. And one of the positive feedback loops that we're talking about today is called the ice albedo feedback loop. So in order to demonstrate how quickly melting ice can actually trigger warming, what I thought I would do is step back out of my apartment. So I'm outside of my apartment again. And just like the last time I showed the white sheet versus the black sheet, well, the white sheet is back. And so I have it sitting on my porch, just outside of my apartment. And let's see what the temperature of it is right now. Okay, so low 70s, 71. Just for the heck of it, let's take a look and see what the temperature of the ground around it is. Dang, 105.
That
So
white sheet's a lot cooler.
There's a big difference in temperature between our sheet covered ground and the exposed ground. Well, this sheet behaves a lot like ice. It's very, very reflective of sunlight. Well, what happens is, as the Earth warms up, this ice begins to melt. And as it melts, it gets smaller and smaller and smaller. So I'm going to fold it. And then let me look at the temperature of that area that was just exposed, or that was just shaded from the sun. And let's see what happens to the temperature over the next minute or two. So this was the part of the land that had just been covered by the ice. And now the ice melted. And so I'm over that little area now. Now let's wait a minute and see what happens to the temperature.
Mhm.
You've noticed it's starting to steadily increase. It's not as warm yet as that 105 degrees that we saw with the land around the sheet. But if you notice, it's beginning to steadily increase. It was, what, 67, 66, 67 when I first started shooting this video.
Just a matter of minutes.
It's now
yeah.
71. Let's wait a few more minutes to see what happens. So 71. Now here's the thing. The temperature of that ice was freezing. And what happens is, as it melts, because the air around it has gotten warmer, what that's going to do is that's going to cause the air right next to that ice to heat up, because the land right next to that melted ice is going to heat up. What that's going to do is that's going to cause our sheet of ice to actually shrink even more.
Mm-hmm.
And the land next to the ice is going to continue heating up. And if you notice over our little area where the ice previously was, the temperature just keeps going up. We're seeing now low to mid 70s, 73. If I were to stay out here for a few more minutes, I'd see 74, 75, 76. So the point is that as temperatures rise, ice begins to melt. Now, as ice begins to melt, the ground beneath the ice, as soon as it becomes exposed, it begins to warm up pretty quickly. I mean, I was out here for just a couple of minutes, and the temperature of that ground already went up 5 or 6 degrees. Now, if I were to hang out here for an hour, very soon, I would see temperatures like that.
Mm-hmm.
Very, very warm.
Mm-hmm.
And so as our ice is melting, that's making the ground beneath it a lot hotter. As a result, the air above that ground is going to become a lot hotter. And as the air becomes a lot hotter, that's going to cause more ice to melt, leading to more heating, leading to more ice melting, leading to more heating. What kind of a feedback loop do you think that is?
Well,
all right. So
that is what is referred to as a positive feedback loop. The idea that heating leads to more melting, leads to more heating, leads to more melting, leads to more heating. And it just triggers off this runaway effect. And if you actually take a look at Arctic sea ice coverage over the past 20, 25 years, it is getting lower and lower and lower and lower and lower. As a result, there's not as much of this reflection that's happening that used to happen because the ice was super reflective. And instead, what's happening is that more and more heat is being absorbed. That's making the Earth even hotter and hotter and hotter. And the North Pole is seeing the bulk of that heat. All right, so polar bear, not that we shouldn't be worried about polar bears in Santa. What does that mean for us? Well, here's what it actually means for us. Meteorology 101, ooh, let me get this out of the way here. Meteorology 101, I actually talk, there we go. I actually talk about this very briefly in my Met 10 class when I talk about the global circulation of the atmosphere. There is this thing known as the jet stream. The jet stream is the boundary between warm air from near the equator and cold air from near the North Pole. The jet stream is really, really crucial because it is both the birthplace and the freeway for storm systems here in the United States. This is where we get most of our interesting weather from. Usually, if there's a big tornado outbreak, the jet stream is partially responsible. When we get storms here, most of the time the jet stream is responsible. And in fact, if you actually take a look at how the jet stream is positioned, usually when we get stormy weather here, it's because the jet stream is nearby. Well, here's the thing. The jet stream depends heavily on the difference between warm air from the equator and cold air from the poles. During the summer months, the poles actually are relatively warm. That actually causes the jet stream to move further north and to weaken. Well, as the Earth has been warming, the North Pole has been seeing the bulk of that warming. That is actually causing our jet stream to both weaken, move further north, and become a lot wigglier. All three of those things are happening. Those wiggles have two main components to them, and actually this graphic right here actually demonstrates those two components very well. This big component right here, where it looks like the jet stream kind of bubbles up to the north and then dips back down to the south, this is what is referred to as a ridge. Meanwhile, over here, this dip in the jet stream, this is what is referred to as a trough. Well, basically what happens is, as the North Pole has been warming up, our jet stream has become weaker, but it's also become a lot wavier. And because of our geography, California has, for the most part, been underneath the ridge portion of this wavier jet stream. Well, the thing is that this jet stream behaves like a freeway for storm systems. And storm systems are basically areas of low pressure that travel along the jet stream. Well, those low pressures that would normally be giving us a lot of our rainfall are now moving to our north, giving areas like Portland, Seattle, Vancouver, and British Columbia, and the Alaskan coastline our rain. They're getting our rain now because our jet stream has been moving further north. So yeah, that results in a drier California. And we can actually see this. So this is just data that was taken from the California Department of Water Resources. This was the most recent plot that I could find. This was actually from, this was plotted by the Bay Area News Group, but the data is from the California Department of Water Resources. And this actually shows the Sierra Nevada snowpack, which is where we get most of our water from. Well, if you actually take a look, we have had some abysmally low years this decade, an abysmally low set of years this past decade. And we are now, just right now, we're barely 61% of our historical average, and it's already March. So we're running out of time. That is a scary reality. We are also becoming a warmer state. While Texas has been freezing, while parts of the East Coast have been freezing, we've been seeing 70s and 80s in parts of California in January and February. So we are also becoming a much hotter California. So we are becoming a drier California and a hotter California. So we're hotter and drier. Adding those two things together, more fires. That has been one of the big consequences, one of the big in-your-face things that we have seen here in California. So I know this is kind of anecdotal. I have lived in California my entire life. I spent 25 years in Southern California and much of the last 10 years up here in the Bay Area. And I will tell you right now, what I have seen in the last 3 years is nothing, or well, let me rephrase that. What I saw before that was nothing compared to what I've seen in the last 3 years. The last 3 years have been alarming in terms of fires. I guess technically the last 4 years, 2017, 2018, 2019, and 2020, have been alarming in terms of fires. I have never seen the sky get as smoky as it's gotten. I have never seen the kind of problems that we've had related to fires. It is a scary reality. And when we have warmer weather and drier weather, that puts us 2/3 of the way to having more fires. The only other thing we need is wind. So who can tell me, When do we usually see most of our fires? What time of year do we usually see most of our fires? Fall, summer? Yeah, it's actually in fall. It's actually the months of October, September, October, and November. So that's late summer, early fall. This last summer, we actually got fires early because of that lightning storm. That caused all kinds of crazy things. That caused what I like to call apocalypse sky. And this was a part of apocalypse sky. Um, where the sky was pitch dark at noon. I remember like being so freaked out by that. Um, well, wind is the third key ingredient because wind actually adds fuel to the flames and actually basically allows them to spread a lot quicker. So, warmer weather allows for brush to reach ignition temperatures. Drier weather allows for more sparks. Have you ever touched anything metallic when it's really, really dry? Get that zzz, that shock? I hate that. Um, I absolutely hate that. Um, on really, really dry mornings when I was on campus, I would always be a little afraid to give my wife a hug as I was leaving because I knew that we both had static electricity and I knew that we were going to shock each other. I told her it was because she was electric. Um, and we both loved that. But no, but it's because it's a lot drier. So drier, and not only that, but that also deprives any brush or any fuel from moisture that would otherwise allow it to quench those flames. So warmer weather allows for more ignition, drier weather allows for more sparks, and then windy weather allows for fires to spread rapidly. Add those three things together and boom, you've got fire weather. And that's when PG&E turns off their power or turns off our power. That is when you hear what's called a red flag warning is issued. That is when you see all the smoke. That's when you see all of that stuff happening. And yeah, that is when you see all of that stuff happening is of because of hot, dry, windy weather. Well, we've had a lot more hot and dry weather lately. We get those winds every fall due to what's called the Santa Ana wind effect. Even though we're not near Santa Ana, we get the same kind of effect up here. It's what we call the Diablo winds. But it's just the same effect, just a different name, more NorCal related. Um, but yeah, we have seen a big increase in the amount of acres burned, and Cal Fires had to spend a lot more on fire prevention and firefighting in the past 10 years. It's been a lot more damage. We're seeing it in places that we've never seen it before. I never thought the Santa Cruz Mountains would catch fire. I never thought that we would see Santa Cruz, Davenport, Half Moon Bay having to shut down, not just due to COVID, but due to fire. Like, that was insane and scary. But it happened last year. Wine country has been threatened. Santa Rosa fire actually spilled over into Santa Rosa in 2017, the Tubbs fire. We had to close campus for a full week in 2018 due to the campfire sending all of its smoke our way. So these are becoming more common. And it's partially because we are getting hotter and drier. So what can you do about all of this? One of the things I was asked in this presentation or for this presentation was just to talk a little bit about action items. So the first thing I would say, and this is a big thing, and this is not meant to be a plug for me, but get educated on the issue. Now, being a part of the Environmental Sustainability Committee, I assume that you probably already have some knowledge about this and you're probably already involved in this a little bit, but I strongly recommend getting educated on the issue. The reason why is there's a lot of misleading information out there. There's a lot of confusion out there. There's a lot of frustration out there, and it really just throws people off. So the more that you know, the more that you can explain this to other people. Um, You can also figure out your own carbon footprint. There's a carbon footprint calculator that I assign to my students. Darn it, I forgot to post the link here. Once I'm done with this presentation, I'll paste it in chat real quick. But there's actually a really useful carbon footprint calculator that you can use to determine how your lifestyle is actually committing or is contributing to global warming. How your lifestyle is actually adding carbon dioxide into the atmosphere. Educating others is a big, big thing. One of the reasons why I got into teaching, other than I just love doing it, is that there's a lot of people who are active in climate science, but aren't talking about it to the general population. And so instead, the general population are left to listen to Al Gore or Joe Biden or Donald Trump or politicians. And even if some of them are actually saying a very noble and accurate message, because of their political leanings, that honestly causes their credibility to take a hit, because many people aren't going to listen to somebody on the other side of the aisle. The second thing, take simple but meaningful steps to reduce your carbon footprint. One very big critical thing I will say, something that I always kind of get about, is when you hear people walking around saying, drive a Tesla, get solar panels installed on your roof. I read an article one place that I forget who it was, but it was an environmental agency. It wasn't EPA. I think it may have been the Energy Information Administration. It was somebody, some climate agency that said, well, if you want to impact global warming, if you want to reduce your emissions, sleep at night with your thermostat on at 85 degrees. When people hear stuff like that, wait, I got to buy solar panels? I got to buy an electric car? I got to sleep with this ungodly temperature? I'm not going to do that. We oftentimes turn conservation efforts into these giant unobtainable goals, and that turns people off. So let me tell you what you can do. In giving this presentation, usually when I give presentations, I usually have a spotlight on me, and I usually have a lamp on so that I have adequate lighting. I actually found out there's a way on Zoom to actually adjust my lighting or adjust how I look for darker lighting. That way I don't have to have those lights on anymore. So I just turn those lights off now. Also, I've made it a habit when I'm not in a room, I turn that light off. Now that might not sound like a big thing. Okay, you turn the light off, so what? Here's the thing. Anza College is a college of about 20,000 students and faculty. If every single person at Anza College turned one light off, that's now 20,000 lights that have been turned off. Now let's expand it to the greater Silicon Valley area. The greater Silicon Valley area has about 3-4 million people in it. If every single household were to turn their lights off, were to turn off one light in a room that they're not in, that would add up really quickly. So finding small, meaningful steps to reduce your carbon footprint. Another good thing that you can do, I don't know if you've ever noticed the little blinking clock on your microwave or the little light on your, I almost said VCR, that shows you how old I am. But that little light on your DVD player or your Blu-ray player or your TV, that's what's referred to as vampire electricity. The purpose of that is just to show you that the thing is plugged in. But guess what? That itself has a draw on electricity, and therefore that has a carbon footprint. If you can take all of those things that aren't ever in use or that aren't regularly being in use, if you can take all of those things and attach them to one strip that has an on-off switch, turn that off every night, you've just cut back on your carbon footprint. I live 2 blocks away from the Starbucks I go to. I usually hit up that drive-through. They all know me. They all know to give me my my Trenta iced coffee with 2 pumps of mocha syrup and half. If I just walk there instead, and I can actually say hi to them in person, even in times of COVID. Um, just doing something like that cuts back on your carbon footprint. Now, if you can get solar panels, I'm not saying don't get solar panels. If you can someday buy a hybrid or an electric car, someday do it. But don't think that those are the only meaningful things. And I think a lot of people get thrown off when they think that. In addition to this, getting involved with local climate agencies. A climate agency that I'm a big fan of is 350 Bay Area. So the purpose of the number 350 is 350 parts per million of carbon dioxide. Basically, for every 1 million molecules, a part per million is one molecule out of the million. Well, right now we have about 420 parts per million of carbon dioxide. Actually, it's 416, just to make sure that I'm being straight with that. It's about 416 parts per million. 350 has been seen as the threshold that we need to be at to be environmentally sustainable. And so 350 Bay Area is this idea, or this agency that's like, let's get our carbon concentration back down to 350 parts per million. That would be a very ambitious thing to do, but we could do it. There's also Climate Action Now California. These are just a few agencies that are part of my list of like things that you can join. So and I really recommend just even taking a brief moment and looking around, asking some other people in the environmental studies department, or asking me about other climate agencies that you could take part of. And then the last thing, consider a political candidate's position on climate change. I don't want to get political. I know I've kind of already gotten a little more political than I wanted to, but I will admit that one of the biggest factors in my vote, in addition to a lot of the other things that have happened in the last 4 years, one of the biggest factors for me in how I voted this last presidential election was the Paris Climate Agreement. And knowing that our previous leader had taken us out of it, and knowing how dangerous that was, and wanting to get back into it. And obviously that's not the only thing that influenced how I voted, but definitely considering a political candidate's position on climate change. And they're usually not going to split hairs about it. They're usually very blatant about their position on climate change. So they're not hiding anything from you. So that's really it. So that's my 30,000-foot overview on climate change, how it differs from global warming, what some of the causes and some of the consequences are. I will be perfectly honest, I literally have tried to take my entire introduction to climate change class and squeeze it into an hour and 15 minutes. So thank you all for bearing with me. I love the questions I've seen asked in chat. I love the interaction. I can hang out now if you have any questions for me, or want to bounce anything off of me, have any ideas, thoughts, questions, comments, concerns. I'm yours.
I just want to give a quick, big thank you to you. Thank you so much for being here and just giving us all this information. I was just thinking as you were speaking that we're not just learning about climate change or sustainability, we also got into like geography and everything that has to, like oceanography with ocean currents. And I've loved every single moment. So thank you so much for being here.
It's such a fascinating field. And there's so many facets to it. Thank you.
I just want to reiterate what Yutong said as well. The presentation was amazing. Thank you so much for coming. And yeah, I texted Yutong and told her that I wish I was staying at the Anza longer so I could take a class with you.
You can always take one online, or where are you hoping to transfer to?
Probably UC Davis.
Oh, okay.
Yeah.
I was gonna say, if you're going to San Jose State, I also teach there. But yeah. And also, if you know anybody looking for a class, I don't shy about adding people who are on my wait list. So if you know anybody who's looking for a class, send them my way. I'm usually very able to add as many people as I can. So I'm able to be very accommodating. So what else can I offer or chit chat about right now?
Should we stop recording?
Yeah.
Thank you.
Bye everybody.